Hello, everyone. I would like to take this opportunity to welcome you all to Cities Knowledge Graph Completion event. Okay, so thank you for coming. I'm Markus Kraft. I'm from University of Cambridge, and this is
Pieter Herthogs from the Singapore-ETH Centre.
And Aurel von Richthofen, currently at Arup in Germany.
So, we will now talk about this beautiful Cities Knowledge Graph event. And Peter, why don't you start the slide set? Yeah. Right. So Friday afternoon, you're probably half asleep. You're already looking forward to a beautiful weekend in this beautiful city, Singapore. But to make it a bit more exciting, we decided to look at a different city. So we're looking at Metropolis. Metropolis is a fictitious city, and unfortunately, we're looking at the collapse of Metropolis. So it was a huge, sprawling city designed with cutting-edge technology, automated systems, home of millions, but unfortunately, everything was in silos. People couldn't really communicate with one another, and the whole place was completely inefficient. And for this reason, everything went wrong. And so we had to face large infrastructure failures, bridges collapse, resource mismanagement, water shortages, traffic catastrophes, and environmental disaster. And of course, somebody has to save this world. So our heroes, Aurel, Pieter, Meiji, and my good self, taking the photo at the time, went to URA, looked at Singapore, identified the problem, and went on to write a proposal to NRF to do an intra-create program that's called Cities Knowledge Graph to save the world and make it a better place. And what you now see is what we presented to NRF. It's a bit of a propaganda video, which has all the key elements in it. And then at least you know what the Cities Knowledge Graph is. So Peter, why don't you play the video?
Cities bring together complex interacting systems of people, infrastructure, transportation, nature, finance, energy, and many more. Researchers at CARES and SEC apply and develop innovative and interdisciplinary methods in order to understand how we can design cities successfully and sustainably. Through master planning, planners shape our cities of tomorrow, determining how people live for generations to come and whether they will live sustainably and successfully. Master planning is an engaging, creative process during which planning experts carefully apply their craft, balancing often contradicting targets to create a unified vision for future development. However, the master plan that guides that vision is a static image of the city, a snapshot frozen between present and future, that does not adequately support the dynamic development of cities. Together, researchers of CARES and SEC proposed to push the boundaries of master planning by developing a master planning knowledge graph, supporting decision-making towards more sustainable, livable, and resilient cities. Planning a smart nation builds on knowledge.
So that was how we started. That was our proposal video. In that sense, it was a bold statement, and today we go over what we did in terms of addressing the points in this problem statement. Before we go into that, we also have some short messages from the SEC principal investigators who could not make it today. That is Professor Martin Rabal, the current PI, and Professor Stephen Cairns, the PI that started the proposal or project.
Hello, everyone, and thank you for joining the completion event of Cities Knowledge Graph. My name is Martin Rauchal. I'm a professor of Geoinformation Engineering at ETH Zurich, and I'm also a cluster leader in the Future Resilient Systems program at the SEC. And about a year and a half ago, I took over from Professor Stephen Cairns, his role as a SEC principal investigator of this project. I'm sorry I couldn't make it in person, but I wish you a great and interesting event. All the best.
Hello, everybody. It's such a pleasure to have this a moment to reflect on the Cities Knowledge Graph project, or the CKG project, to give us a required three-letter acronym. I can't think of many projects which are so prescient. Not only is it linking the emerging possibilities of AI and large language models, but it's connecting these possibilities to the idea of a vibrant city. This is the city that brings people together in surprising and creative and enjoyable ways. This is the famous mixed-use city. I think it's a wonderful example of an intra-create project. I'm really, really delighted and proud to have been part of it. I'm sorry not to be there in person to celebrate, but I'll be following proceedings from afar. Thanks, everybody, and I hope to see you again soon. Bye-bye.
Okay, these were the opening statements. To quickly go over the agenda, so we have covered the first point. I will start with a presentation about the Cities Knowledge Graph project and its planning applications. We'll then have a break where you can also try several demonstrators. In the second part of the program, we'll start with a presentation by Dr. Aurel von Richthofen, and we'll continue with a presentation by Professor Markus Kraft, talking about knowledge graphs and the world avatar in a broader sense of applications. We will close, and then we will have dinner and drinks. Okay. So, welcome everyone. I'm Dr. Pieter Herthogs. I am project leader and co-investigator of Cities Knowledge Graph. I'm a senior researcher at the Singapore-ETH Centre. That's ETH Zurich's lab here in Singapore. And I'm also an investigator in a couple of other projects. Particularly, I do research on design evaluation and knowledge representation for urban planning, as here, urban design and architecture. Now, the keyword for Cities Knowledge Graph is synthesis, because city planning is a process working towards synthesis, in which planners create or try to create coherent consensus between targets. Planners need to take into account several themes and goals. They need to take into account the built environment, housing, commerce, industry, mobility, sustainability, etc. And they come up with proposals and regulations that help get us forward, help create better cities, better for people, better for business, better for many targets. Now, this bringing together, this integrating of all these topics, of all these domains, is still being done much in the same way as before. Yes, there's a much better understanding about our systems, our mobility systems, our housing, and how that works. There's more science, there's more tools, there's more simulations. But in the end, bringing it all together is still done in quite a similar way, in quite a manual, craft-based way. And so Cities Knowledge Graph wants to support this bringing together, this synthesis in a digital way, using knowledge graph technologies. In that sense, there you will see aspects here of, I'm going to move the microphone a bit. You see aspects of planning applications. That's the top part of the diagram. But of course, underneath sits a knowledge graph, a representation of domain knowledge in order to structure data in a way that is more interoperable, that can synthesize better. So you might wonder, what's this knowledge graph? Well, most of you use knowledge graphs on a daily basis because it powers technology that brings together multi-domain data. When you do a Google search and you get this summary as a panel on the right, that's Google's knowledge graph panels. That is a synthesis of data from various sources in a easy to comprehend way. When you're using an AI assistant, there's a system there that understands concepts and meaning. You ask it a question and it understands or sometimes doesn't understand you, depending on which concepts the system knows. In that sense, it can synthesize what you are talking to or what you're asking about, and it knows concepts from all kinds of domains. So knowledge graphs support synthesis digitally by enabling interoperability, that's a key word, between domain knowledge and data. So when you're doing land use planning, obviously that has an effect on mobility, that has an effect on energy, but also mobility will have an effect on planning, etc. So these domains, these systems, they are not separate, even though they might have different agencies or different types of professions dealing with them. And in that sense, you create silos between them. So what we set out to do is to make knowledge compatible by bringing different domains and their data together and by integrating existing and new knowledge. That's what these approaches are made for. Secondly, we make knowledge accessible because once you have a representation of your knowledge, you can search that knowledge, you can retrieve certain data, and you can integrate more by automating things like evaluations or simulations or data processing, which makes knowledge more accessible. Thirdly, these approaches make knowledge explainable. They bridge between human and artificial intelligence. You represent knowledge in ways that a human understands, but also that a computer understands. And that's very powerful, because then you can bridge the gap between both. Also, because you have this formal representation, you can do things like validate statements and assumptions, or support reasoning and learning using these technologies. So a central concept or artifact that we use is the ontology, which is a representation of the concepts in a certain domain about a certain topic and the relationships between them. So here you can make an ontology for US presidents. And so you have a president. If a president is married, then he has a first lady. If it's a US president, they will have a place of birth. They will have a country they're president of. They will have all kinds of data. But rather than just storing the data points separately, you're storing as well the meaning of all these categories. So you add a layer of abstraction in order to understand things better. We're not interested in US presidents, we're interested in city planning. So you can do the same for planning regulations, for example. So you can say, what's a zone? Is commercial a zone? Is commercial use a land use? Does a commercial zone allow a commercial land use? What's a restaurant? Is that allowed in a commercial zone? Etc. You can even model in quite advanced, let's say, exceptions. Like in this part of town, you can do 40% hotel use, while in another part it might be more. These are all things you can model using ontology. What you can do with that is build more advanced applications like a search engine for regulations. And I'll show you an example now.
Site search is a common planning task. Planners often need to find sites for a particular development. What and how much you can develop on a particular site is determined by various regulations. Currently, Planners need to manually go through many types of regulatory documents and web pages to determine what could be developed where. They need to consult dozens of documents for each plot they want to consider. To support site searches in Singapore, we developed a programmatic plot finder application using our knowledge graph. This is a search engine that can check planning regulations. Instead of manually verifying dozens of regulatory documents per plot, a single search returns all relevant plots across Singapore. One search can replace close to 1.2 million human verifications.
So in that sense, the benefit of representing your knowledge in a way that a computer can use is that all of a sudden you can check regulations for the entire country rather than for a couple of plots. So knowledge graph technologies support a wide range of applications. It's not just the one I just showed. And so we've also, as part of the project, explored several possible use cases, ways in which these approaches can benefit planning. And of course, we did that to varying extents. Some became full demonstrators, others are just a small exploration that led to a publication. But so we looked into ways to make knowledge compatible, for example, bringing various city data together in one graph and representing planning regulations, but also into accessibility, automating site search, integrating mobility simulation results or energy simulations, and also about the explainability of this knowledge, quantifying impacts of proposals, validating ontologies with stakeholders, that's the URA mainly, and exploring reasoning by knowledge graph agents on this planning knowledge. When I talk about we, that's us. So it's a sizable group of people from various backgrounds. Cities Knowledge Graph is a 3.5-year NRF-funded intra-create thematic grant project. The intra-create projects are meant to bring together partners of the CREATE program. You're in the CREATE Tower, so that has top universities from across the world, as well as the Singapore universities. And you come together in a way that bridges a gap between knowledge, between people, between experience. In this sense, we have knowledge graph technology that was being used for carbon emission reduction, chemistry, and these topics. And you have the city planning and urban research background of CSCC's future city laboratories. And if you bring those together, you get Cities Knowledge Graph. Now, if I highlight one thing for today, that's the main difference between what we do and how we do things and how planning applications are conventionally made. So conventionally, a team or a department or an agency or a research group might make a certain application, and they have a certain application in mind. And in order to build that application, they'll use data. Usually everybody uses the same publicly available data, at least in research, in order to build their particular application. But in order to do that, they interpret what that data means. You have certain values in these data sets, but they give it variable names. They might use some data point as a proxy for something else without actually documenting that formally and in detail. That's good if you're making one application, but of course, everybody interprets these data differently. They add their own custom data semantics to the data sets, which as a result means that the applications they make are incompatible. So there's no interoperability between these tools. In a knowledge graph approach, and the approach we applied, we invest heavily in creating general data semantics, as you see on the right. So you invest heavily in creating a common knowledge that applications can use, either new applications that you make based on that knowledge base, or running existing applications using the data that you have stored. Of course, this requires quite a bit of work because you need to represent all this knowledge formally. So as I mentioned, if you're doing one application, the right method is not the easiest. But of course, when you're integrating all kinds of methods, tools, results, data sets, as many of us need to do now, then you get the benefit of having this compatible knowledge representation on which your data and your data representation is based. In that sense, you get a kind of snowball effect. In the beginning, you do a lot of work, but every other application you add is compatible with everything you've done in the past, and everything that you did in the past is compatible with all the new things you add, which is not true for the conventional one-by-one approach. And that is very interesting. So today I'll present the Cities Knowledge Graph project in two parts. First, I will illustrate background concepts, and then I'll showcase Cities Knowledge Graph based on 3 types of planning actions that we supported. So first, a little bit of background about the semantic web of linked data, ontologies, and knowledge graphs. So these approaches are related to web development. And in terms of computer science, you can see this in terms of adding semantics to web technology. So you have the idea of the semantic web of linked data, which was developed to add meaning to the World Wide Web. This idea stems from 2001, was coined by Tim Berners-Lee. And so he says that the semantic web is not a separate web, but an extension of the current one in which information is given well-defined meaning, better enabling computers and people to work in cooperation. Back in 2001, a web page was simply text. You had pages that linked to each other, but a computer had no idea what was on the web page. Of course, this is completely different now, 22 years later. A computer knows what's in the web page. It can refer to certain paragraphs, sentences, where it retrieves certain information. So you see, a lot has happened in terms of these developments. But you see that this aim to bridge the gap between humans and machines has always been there, because you create a shared knowledge representation. So adding machine-readable meaning to data on the web creates a web of data rather than a web of documents like it used to be. It enables machines to search and interpret the web to act as functional agents, what we now usually refer to as assistants for people. If you create these knowledge representations, these ontologies, and you add data to them, you get linked data, and also often called linked open data, or at least a part of it is open, because of course, if you make knowledge representations and if this takes time, you want this knowledge to be open. You want this knowledge to be reused by others so that they speak the same language, so that what you do is compatible. I'm sure that big knowledge graphs are very closed and in big tech corporations, but there is a great effort in this community to create open data and open knowledge. So how does this work? Let me illustrate this. So maybe there's knowledge in the Singapore-ETH Centre, and that can be represented. So you can represent the center itself, and you can say a fact about it. It's located in Singapore. So you get 2 pieces of information and a relationship between them. The Future Cities Lab Global program is a part of the SEC. And then you have somebody else with their own domain knowledge, maybe geography, and they know that Singapore is located in Southeast Asia. In a web way, you represent all these things as links, as URLs, if it's a web page, but we use IRIs. Basically, you have a location where the definition is stored, and you have locations where the relationships are defined and stored. So you see that there's a page for the SEC, there's a page for Singapore, there's a page for Southeast Asia. Of course, if you're referring to the same page, you can link the knowledge and it can become one graph. If you want to add more abstractions to that, you can add ontologies so that you can define, well, the SEC and FCL, they are research entities and Singapore is a country. Because then maybe you can do particular reasoning for other countries or other research entities. And so ontologies add a layer of abstraction to help classify your knowledge so that it's more universally usable. And this allows you to do certain feats of reasoning. This is not really a feat in this example because, yes, we know that Future Cities Lab is located in Southeast Asia. But it's these kinds of transversals of logic that are enabled. And of course, if this graph is much bigger, if it's something you don't know much about, then you can do this. Well, you can do this. The computer can do this and can tell you what it reasons about the knowledge. So the technologies that support this kind of work are called semantic web technologies, and they promote common formats so that people can develop knowledge in similar ways so that their knowledge is compatible. So here on the image, you see the semantic web stack, and that's a stack of technologies for all kinds of things you would like to do, making ontologies, transmitting things, ways of storing data, querying data. So there's many options. In that sense, it's a community and it's a collaborative movement led by the international standards body, the World Wide Web Consortium. And these are also the technologies and approaches that we use for cities knowledge graph. In that sense, this approach is domain agnostic. You can apply it to anything. We happen to apply it to city planning and cities knowledge graph, but you can do anything because you can do this for any knowledge. So if you can do it for anything, you can also do it for everything. So you could do it for the world, hence cities knowledge graph being a project under the banner of the World Avatar, which Professor Kraft will talk about in his seminar. And so you can do all kinds of topics. You can do chemistry, you can do different countries, you can do real time, you can do discrete, anything you want. But in our case, we do translations from planning to knowledge graphs. So an example here is you can go from a planning regulation like the street law plan from Singapore, which gives you information in a certain format, but it doesn't contain formal definitions. You can translate that into an ontology where all the concepts are defined using this persistent IRI. And basically you get a representation of this regulation that the machine can use and that a human can use. So if you then have this particular regulation, it is attached to other things that happen in the city, and so it will also be attached to other parts of your knowledge graph. So you might find that it's related to the master plan, that it's related to mobility simulations, to time series data you captured, or to a building information model that happens to be in that particular area. And so if you look for a concept within the thing you're dealing with, you can find information about that concept throughout the knowledge graph and the parts of this graph that you've attached. Knowledge graphs refer to large living and learning graph databases, particularly databases where the instances, the number of data points, largely outnumber the number of classes, the number of concepts in your ontology. And it's a term that's popularized by Google in 2012 when they launched these side panels that you see on the right. The concept of knowledge graphs sits within artificial intelligence, particularly important to the field of knowledge representation and reasoning. So if you Google and you type in this linked query, my example here is who's the father of the wife of the king of Bhutan? You get an answer, and that's because in the background, there's a system that knows what's Bhutan, what's a king, what's a wife, what's a father, and how are these related. That also means that if your underlying model has errors in it, you will get wrong answers. So if you make a very simple ontology and you define a pizza as something with a topping, then a computer will think ice cream is a pizza. In that sense, it's important to be rigorous in how you develop your knowledge. And of course, that means it's important to reuse knowledge because it takes investment. Knowledge graphs, when we started, was at the top of the hype cycle for AI. That also means that, of course, we are exploring ways in which this can be used. And city planning is a particularly interesting application because it relies so much on interoperability and synthesis. Ontologies, knowledge graphs, and semantic web technology enable the branch of AI that's called symbolic artificial intelligence. Most of the media attention goes to sub-symbolic AI, that's the generative stuff, your DALIs and your ChatGPTs. They represent what they see from real data, sensory data, and they represent it as numbers, as vectors. So it's quite opaque in that sense. In a symbolic AI approach, you represent an apple in this example as actual understandable sub-concepts or related concepts to an apple. So you can see what the color is or what the dimensions is. In that sense, symbolic AI approaches are particularly good for search, decisions and validation, and planning. So let's showcase how knowledge graph applications can support synthesis in city planning. Firstly, that requires to kind of define, well, what is city planning, because that's already quite a broad topic. We did this literature review, and there, in order to do the search and define this better, we defined 4 planning actions or meta practices of planning: representing things, evaluating things, projecting or creating things, and synthesizing knowledge. Because, of course, a lot of the literature might talk about semantic web in cities, but not necessarily think it's related to planning, but it could be useful. That's why we introduced these 4 meta practices. And in that sense, those are the ones we look into in terms of demonstrating support. So the act of representing things has the example of site search that you already saw a little bit of. Evaluation goes into site evaluation, and projection goes into impact assessment of your creations. And of course, they're all being supported by a synthesis approach, because that's, of course, what we do. When you do planning, when you do anything, because these are 4 quite generic categories, you do all these things continuously. You can't represent without evaluating, etc. But of course, there are actions that are mainly one of these practices. So you need to start by representing knowledge. What we did was represent Singapore's land use planning regulations, or at least a good chunk of it, starting with the master plan. So in that sense, what we did was develop a measurable representation of the intended future city, because that is basically what the master plan governs. You get the bounding box, as it were, or the boundary conditions for development, at least for the next 5 years. So we're using artificial intelligence to explain the rules and assess regulations. That's a question. Of course, if you equate AI with sub-symbolic AI, that might be difficult. You might wonder, well, can't ChatGPT do this? Well, they tried it out at URA and it can't. It doesn't understand the rules. It gives you rules from other cities. So in that sense, it's hallucinating about what is allowed where. And you don't want it if you want to automate your regulatory system. You don't want a computer system that gets things wrong, which is why we focused on search with a symbolic approach. And so I'll continue with the example.
Instead of manually verifying dozens of regulatory documents per plot, a single search returns all relevant plots across Singapore. One search can replace close to 1.2 million human verifications. For example, let's search for all plots that allow a development that includes a clinic, flats, and a mall. After selecting these 3 programs, we can specify a minimum required gross floor area for each. Clicking the Search Now button gives us all the plots in Singapore that could allow our set of programs or more.
So you can search across the island, finding the plots for your particular development, and not just a particular zone, but also a program and an amount of program. And so it's different levels of regulation that have been represented, but also workflows that we developed to determine how much you can build, what are setbacks in certain plots. So this entire process that you normally do for a couple of plots, because it takes a lot of work, has been automated. One thing you also notice is that 3.5 years ago, we were still using a Cambridge-trained British narrator for the video, but now that has been replaced by an AI. So what you see here is one application made using our knowledge graph system. And so you can do more things. In that sense, it's the kind of tip of the iceberg in this diagram, which is a simplification of our architecture, but it follows the layers of the main diagram. And at the bottom sits a lot of knowledge representation, a lot of ontologies and data sets from which we can build these applications. So the first rule of ontologies is reuse existing ontologies, because you don't want to make new ones if you don't have to. So in terms of representing 3D shapes, we reused and improved on ontology for the CityGML standard. That's a standard for 3D city models. That's already a schema that's very formally defined. A group in, I think, Geneva made an ontology of that. We used that ontology, we improved it, and that became the basis for our ability to display 3D cities. Sometimes when there is no formal knowledge available, you need to model it. And in that sense, that's as simple as drawing a diagram, linking the concepts that you know in a certain domain. So we made an ontology for Singapore's zoning, land use, and program classes. So here on the left, you see the written statement of the master plan that tells you what kind of land uses you're allowed to build in certain zones and gives you examples of buildings or activities that can take place there. That's what we call program. And so we go from a document like that, and of course also this colored master plan, to an ontology that represents these formally in terms of what allows what, how much percent of what. All these rules can be formally defined so that you have a representation of this institutional knowledge. You can also generate ontologies. You don't always have to model it all and spend like half a year thinking about what is a plot. So we generated definitions for mixed use in Singapore, because mixed use is something that is in a lot of developments. It has a lot of benefits, but what is mixed use? And you want to know what mixed use is if you need to simulate the energy use of mixed use or the mobility patterns that mixed use generates. And so in that sense, we used Google Maps data to look at, well, what kind of commercial places are in a mixed use development, and then use clustering to get 163 representative archetypes so that you get a lookup table. If you need to do some kind of modeling, whether that's just master planning or energy modeling or anything, you have these archetypes to fall back on rather than just guessing. So in that sense, you have an automatic generation, and these archetypes just slot into the ontology. You have new definitions, and they're related to the existing official knowledge. As I mentioned, another thing we did is create workflows to estimate allowable gross floor area. So in planning deals with how much of what should be built where and why. The why we leave to humans, but the rest we can automate. And in that sense, what you can build relates to land use and zoning, and where you can build it as well. But how much is a very important thing, because that gives you your surface areas. But those regulations become more complex. They're about how far from the plot border can you build, how high can you build. There can be many regulations that govern a similar thing, like building height. And so we created a workflow that determines how much you can build of which land uses. So in that sense, it becomes a 3D land use planning map and data set. What you need for that is an ontology of URA's regulations. So that's what you see here, although it isn't that readable probably. So basically, it tells you which rules come from which kind of regulation, which specific document, so that you can see, well, this particular gross floor area for this particular plot, for that particular land use, these are all the documents that have been used. And so when this video states that one search replaces close to 1.2 million human verifications of documents, we actually know which exact documents need to be checked for each data point. You can make search engine with that, but you can do other things as well. So you can ask all kinds of questions because you have that knowledge representation. So which regulation allows worker dormitories? What's the average allowed building height across all URA regulations? Or in case of the example here, which URA regulation allows absolute heights of more than 100 meters? And you can query for that. The query you see here is basically in the front end of our backend. That's the direct query into our Blazecraft-based knowledge graph. So the applications you see are all front end, so that you don't need to kind of code these queries, but you can do that directly and answer these kinds of questions and build applications with them if you so want. Third ontology is the buildable space ontology that governs basically building characteristics, height, floor-to-floor height, gross plot ratio, site coverage, all these things that are in the regulations that have certain values allowed by certain regulations that differ depending on the area, depending on the regulation, depending on the building type. And so there's formal regulations, there's formal descriptions for all of these so that nobody ever has to interpret what is a setback anymore, that you can just use this ontology or building height or etc. And that also, aside from the site search application you saw, supports new concepts. So you can ask questions again to the knowledge of all these regulations. What's the setback at first story of an allowable buildable space? Which URA regulation has defined allowable buildable space the most times? Or which plot has the largest buildable space by area for student hostels? So you can retrieve all kinds of things with a great level of resolution. In that sense, this knowledge representation and the data that we link to this has two benefits. So on the left side, in terms of representing zoning, you get a novel representation of the institutional knowledge of a particular domain. So you have this representation that is readable by humans and machines, which also allows you to do advanced things like search, but also, for example, allows you to compare different versions of regulations. If you're making a new master plan, if you're proposing a change, you can see how that change affects things. On the right, in terms of the two other ontologies in the workflow to generate allowable gross floor areas for Singapore, you basically get a new workflow, novel workflow and dataset. So you get this data set out of it, but you can generate that data set again with different rules if you propose different rules. In that sense, it becomes easier to quantify impacts of regulatory changes or derived impacts that are based on GFA, like energy or mobility. So you get a quantified, measurable 3D master plan, as it were. Fourth thing that's important about ontologies is validating ontologies, because of course we can model it by ourselves, but it's good that experts also look into it. So we have verified our models of planning knowledge with domain experts from the URA. And in that sense, you basically go through what are all the modeling decisions made, because making an ontology, making a representation of knowledge is a modeling process. You have scoping decisions, you have ways of doing these things, and these things also need to be verified. Is it correct? Are the assumptions correct, etc.? So that's also part of the process. Finally, in the diagram, you have this agents layer, and that's the automation layer. So you have agents that pipe around information, that import data, that export data to help visualize things. I think Markus might cover more of these kinds of agents, but basically they are what automates our processes. We've described this in a number of papers, including this one, which came out last week. So That's probably the last one within the project duration, but that's always nice. And these agents enable us to import, update, augment, and visualize city models. Okay, let's go to the second way in which we support city planning, that's site evaluation. And I'll continue with the video.
Using the programmatic plot finder application, we can easily find all relevant plots, but this still leaves many options to choose from. In a site search, planners also evaluate the suitability of different plots based on multiple factors. To help with this, we developed our Suitable Site Selector application. When we switch to the Suitable Site Selector, we can compare up to 5 plots side by side, allowing us to compare relevant information for each plot and its surrounding area, which includes all plots within 500 meters, representing a 7.5-minute city. To help select a suitable site, we can compare available information about present conditions, potential future conditions, and differences between present and future.
So it's not enough to just find sites where you can do things. You want to find the best site, right? Or the most affordable site, whatever best is for you. In that sense, we created this extension of the first demonstrator, showcasing multi-domain data and bringing it together. Also the differentiation between present and future, which is something we have to highlight quite a bit. Planners are quite used to dealing with the future, like a master plan is about the future, even though it exists today. But in that sense, it's important to see what's there now, what's there in the future, what's the difference, how many parks are there now, how many parks are allowed in my context, according to the regulations, these kinds of things. If you have a good idea of what you actually want to achieve and what is good for a certain goal and bad for a certain goal, you can automate quite advanced evaluations. So we did an exploration where we automated SWOT analysis for sites based on the goal of photovoltaic energy potential. And so we categorized the indicators there and categorized them as strengths or weaknesses, opportunities or threats. As an example of once you know what is good and what is bad, you can of course automate an evaluation across the city. Other ways of evaluating is integrating different domains. So for mobility, what we did is integrate MatSim output file. So MatSim is an agent-based simulation. It's basically a computer generating little agents that want to move to certain places in a city. And so they try to find the best trajectory iteratively, and it's maybe millions of them searching this. And in the end, what you get is traffic jams and good flowing traffic, things like that, with different modes of transport, and they all try to optimize their routes. You can imagine that such a simulation is a giant data set of people moving about. And typically, what happens is that a MatSim expert does such a simulation, analyzes particular questions that maybe a transport agency has, and then gives a report. But actually, there's a lot more answers and questions in that data set. And so in that sense, what we did was integrate the data set and make it queryable, make it tied into land use planning questions. So normally you have this one report coming out of the models. The model is kind of out of the loop of the user and the expert. And in our case, we integrate the model output so that a user can directly query it, so that you can develop new indicators that are more related to land use planning, for example. So that unlocks this data and makes it accessible for planners directly. Thirdly, we talk about projection or creation of new proposals and their impacts. So in that sense, the example there is impact assessment. So if I propose something, what are going to be the impacts on certain topics? And so as mentioned, because we have representations, computer readable files of regulations, one thing you can do is change them and see what the impact is, because we can also calculate the gross floor areas, the density they allow. So you can, for example, say, well, the height control plans in Singapore, they allow an extra story. What's the impact? And so you can rerun the workflow that we did, and you get the result. This is a regulation that affects about 3,000 plots, but there's actually only 54 that would gain extra height, because height is governed by a lot of regulations, not just this one. So in that sense, you can see, well, we make a change. There's actually a small impact. It's only 75,000 square meters, but all these values run out of the system. And you can see, oh, where in space is this? Like, which areas benefit from it? So in that sense, it's a very different way of analyzing a proposal. This is, of course, just a parameter change, one extra story, but you could propose, I don't know, build form regulations that relate to urban heat or to rising water or something like that, and then see what changes when we implement these rules. And changes in terms of gross floor area, which you can then equate to mobility or money or whatever you want to equate. You can also simulate. So we've automated simulations, integrated the city energy analyst to run energy simulations on building footprints and land uses. That's the kind of inputs you need there, so that you can calculate, well, what's the current expected energy use, but also, as we can calculate potential new GFAs for new uses, we can also calculate the energy uses for those. And finally, another thing that we've worked on and will continue to work on is an urban metabolism ontology, to have a more general way of dealing with these kinds of equations as to what is the present and future resource use intensity, because electricity is one of them, but it can be water, it can be the circular economy, so construction materials or food waste. They're all urban metabolist processes, and so it would be good to have a kind of general framework to deal with them, so that you can compare the present with the future or various proposals that you might have. That concludes the overview in the two parts. And I will go on to some reflections. I also see it's 4 already. So as mentioned, knowledge graph supports synthesis digitally by enabling interoperability. So I hope with the examples, it became a bit more clear why this approach makes knowledge compatible, accessible, and explainable, and what the benefits are of investing in this underlying knowledge representation. So it demonstrates that we can support synthesis digitally, but yeah, so what's next? See, this being a completion event. And in that sense, we can, of course, make more knowledge compatible, integrate more domains, create more tools. But another thing that is probably going to be very important is to make the knowledge more accessible, and then particularly automating the creation of knowledge, the creation of ontologies, or the updating of ontologies, the maintenance of this knowledge, because it's an investment, and the more affordable or accessible we can make this approach, the better. In that sense, the combination of things like large language models and generative approaches and ontologies is currently very hot. So that there's definitely going to be a lot of work related to that in the future. Most importantly, I think, is making knowledge explainable. And I think in the future, based on what we've done and what other people do, we can definitely leverage on the open and formal knowledge that is created. There is great power in having a representation of how things are done. It makes it easier to train the next person. It makes it easier to talk to somebody else. And part of testing these approaches is also seeing what you can do with it. Because yes, okay, it's people talking a bit too long about certain definitions or being nitpicky about what do you exactly mean. But in the end, you can build quite advanced technologies, and you can build it in a way that bridges the gap between how humans do things and how computers do things, which is very valuable. And in that sense, the more of these approaches we develop, the more we find out, the more we can build on mutual understanding. And you saw a lot of work here, and that work would not have been possible without this amazing team. So thank you, everybody, for the work and your attention. Considering, so there's a little bit of time for questions.
Do you have the slides for the showcase?
Yes, I do.
Okay, great.
Considering that we'll have a break and demonstrator session after this that the digital audience can't attend, perhaps maybe we should look if there's any questions on the Zoom first.
Nothing yet.
No questions. Are there any questions in the room? Yes.
Very impressive. But I was just wondering, how do you actually then capture, because I noticed that you've got all the rules and regulations of URA, but there are many other rules that I don't seem to have captured in, for example, National Parks Board. They have their tree conservation area, and they're actually working on quite an interesting project now called ecological profiling, which means that they're now looking at all the natural areas. And that's one thing that I think cities are doing now, looking at what are the natural areas, how do they actually conserve biodiversity in a city, which is very important for health and various reasons. So I suppose it will be very difficult once that information comes out to actually incorporate it.
Yeah, so the thing there is everything can be added, but it needs to be added. Like you need the onboarding, it needs to happen. So in that sense, it's possible, it's necessary for certain assessments and policies. Currently, it's not in the things you saw, but that doesn't mean it can't be, that doesn't mean it can be extended, because in that sense, incremental development is one of the main standards of these approaches, because knowledge always changes, so you'll always want to be able to extend and upgrade. So yeah, in that sense, there are, of course, things not in the, there's themes and domains that we haven't integrated and that need to be integrated in a full model or for certain applications. But that it can happen, so let's make it happen.
More questions? Maybe just, I like science fiction, as you may have already noticed with the start of this event. If you think about it, that in a few years, these regulations will be in that format, then you can automate an awful lot of administration. It will completely change the speed at which we can go through a planning process. And this is not just planning, basically touches upon every law, every regulation that is used in many other, or in any other area of human life. So given, like, this was a hand-curated process, but it was just done by us, given that similar efforts now can be seen anywhere in the world, and many, many more research groups are joining, probability that this happens in the next 5 to 10 years is super high, and that would, it is already clear that that will lead to a complete change in the way we can administer a society. But of course, for that you need money, and we are now in the process of trying to find new research proposals, but also working with directly with industry to take this further. It is of course also clear that we have to always demonstrate an additional sort of benefit, and we wanted to use part of this event to show you in sort of hands-on demonstrations what we think can be done on top of what you just seen that Pieter so nicely presented. There will be food and drink outside, but there is also a number of demonstrations. Pieter, let's just quickly go through the demonstrations. So we have 6 stations. So I encourage you to go there, talk to the people who stand there. They will talk you through it. So the one is the plot finder. I think you have already seen the plot finder featuring in Pieter's talk. And then the next one is sort of this is part of the World Avatar project. This is a bit more general. This is an attempt to pull as many applications into the city representation, and this is the NTU campus. And John will tell you more about it when you go there. Next one. So this is about flooding. In fact, this is a project from the United Kingdom, University of United Kingdom Digital Twin, where we want to look at the damage to the infrastructure and how that propagates through the networks of water, the telecom, and gas and property. So Markus will tell you about this. And Shinze, he will say something about my hometown, Pirmasens. So this is where I'm from. So he will also demonstrate how you can pull in various application areas into one city representation quite comprehensively. The beauty about that use case for us was it is big enough to exhibit the typical characteristics, but small enough to be able to be handled, unlike Singapore, that is really big. And so this acted so to say as a sandpit. And then so far you have seen external cities, but now we go into buildings. And so there will be one, Aurel and Sandra, they will demonstrate what you can do if you actually move into a building, how that can be represented in the building information models, how you can put that into the knowledge graph, and how you handle live data and even control the building. Next. And you heard earlier, there is no limit to what you can represent. So we also represent quantum chemistry and chemical species and chemical reactions. And Pieter has already mentioned that question answering system, large language models are up and coming. And what you see here, this is at the moment a question answering system. We call it internally Marie 3.0. And there are a number of machine learning techniques. At the moment, we're working on Marie 4.0. ChatGPT has changed the question answering community enormously. Anyway, have a look at what these systems can do. And now, with that, I would like you to move over, have a look. There is some food. Be fast, because otherwise I will eat it all alone. And yeah, so okay, let's adjourn, and we will call you in
half an hour.
In half an hour. Okay.
Yeah.
This is all building inside the building, how to handle life.
online audience. Welcome back after this exciting break with demonstrators. I see part of the audience is still captivated by the possibilities of the knowledge graph. But to not keep our colleagues and audience online waiting too long, and also in light of time, I would like to start. My name is Aurel von Richthofen. As you've seen before, I was the co-initiator of this project. And in 2021, I moved back to my hometown, Berlin, in Germany, where I now work for the engineering company Arup. And I'm very happy to work there and to lead the cities team, where we can put some of the research findings of this project into application. So I'm actually going to give you a perspective from outside of academia, as perspective outside of Singapore, but I hope it helps to contextualize the relevance and also the importance of this project. So let's go ahead. Why do we really care about digital urban solutions? And is there a mandate for this? So next to just pure intellectual curiosity that might drive academic research, is there something out there that mandates this type of work? So first and foremost, I think we should not forget that we still have quite a few challenges ahead of us. So the International Panel on Climate Change repeats that technology, in particular digital solutions, are a cornerstone in tackling and mitigating climate change. And the second aspect is that citizens, including you, produced vast amounts of data, and the value of that data economy is estimated at some 325 billion euro, or 2.6% of the GDP in Europe, and it's going to increase. But the problem is that this data is often siloed and not accessible. So this value can hardly be unlocked so far. What else do we want to look at? The digital twin market globally is expected to grow tenfold, from 10 billion to 100 billion by 2035. The EU share of this is expected to grow 4 times. These are figures that you can contest, but they're still very big numbers. And very precisely, because this money has already been allocated and is being redistributed in Germany, is the so-called smart city model projects, where 800 million euro or 1.2 billion Singapore dollars are being spent on helping German cities transforming digitally. So this is the part that my team and I are looking at in Germany, and we're already working in that space. Another mandate stems from global, regional, and local levels. So the Paris Agreement focuses on global climate change. The UN Sustainable Development Goals also formulate 16 goals. One of them, number 11, says that cities ought to be sustainable, inclusive. And this goes further down with the European Green Deal, which combines sustainable transformation and digital transformation. And as maybe less known outside of the planning circle, the new Leipzig Charter mandates cities to be sustainable and for the people. The EU taxonomy is giving a framework for investment to be targeted to actually be sustainable and not just greenwashing. We see things such as Horizon Europe, the new European Bauhaus. And then again, on the German level, we have Germany's commitment to climate change. Germany wants to be climate neutral by 2045. And this is a very strong effort that the industry is taking very serious. And then the aforementioned smart cities in Germany, where we already see a very big amount of money being invested, but also things such as the open data law. So Germany mandates that all public services, from a marriage certificate to a building permit application, ought to be online accessible. And we're not there yet. Somebody has to help Germany do this. So what are the needs of cities? Cities obviously are many things, and I'm not going to define them here. But one of the needs repeatedly being discussed in the context of smart cities is that we have to move away from the image of lonely islands or silos. We have to connect them, and this is why there's a little steering wheel in here, we have to be able to govern them. But the cities obviously cater for their citizens. So whatever platform we design has to be designed by the citizens for the citizens. And because many of the things that we talk about have a long duration, a master plan is like 5, 10, 15 years into the future, a vision plan, 25, 50 years into the future. Many processes are not visible. We don't really see energy flows. And because of the complexity, we need to have a tool, a system that translates it, that allows us to interact with it in both ways. Cities also need a super search engine. Cities, that's an unknown quantity. We still have to understand what the different components of cities are all about. We may have a lot of insight and domain knowledge about, say, mobility or energy, maybe also how the two are connected. But as Peter has drawn out previously, there's so much more to cities. So we first have to find a way to understand it. And cities administrations, which would be our clients in this case, also acknowledge this. And then they would want to know how to find information that they know it exists, but they don't really know how to retrieve. Modellprojekt the Smart Cities is something that I want to show here because I think it's quite it's a unique opportunity in Germany, and it's a model, I think, for other European countries as well. So far, Germany has already awarded 73 cities or regions the status of model project. This entitles them to particular funding that they have to match. We're talking about 5 to 10 million euro per city. And they can develop their own strategies, their own platforms, and their own applications. Germany is known to be a federal state, which means that there's a competition amongst the cities. And this is nurturing an ecosystem. So there's not one approach to rule them all. In fact, there are many competing approaches. And I'm coming to another point. These have to be open source. So there's a platform that allows cities to connect with each other, to learn from each other, and to replicate or transfer ideas if possible. There's EU funding, there's industry funding, there's urban tech startups, etc. So we see an emerging ecosystem around cities and digital transformation. In order to look a little bit deeper into this, we were commissioned by the city of Regensburg, which is a university town in Bavaria, to assess all digital urban twins under development in Germany, and we've identified 89. And we came up with a framework to look at the technical, organizational, and financial KPIs that enable cities to go on the digital twin adventure. This spectrum shows what cities usually go through. So they all start on the left-hand side in the so-called smart city strategies, because they differ from city to city. There can be an emphasis on ecology or climate or people or industry, depending on what the origin and what the need of the city is. And from there, they usually brush up their geodata portals. We have this in Singapore as well, the URAscape. They engage citizens in participation to hear what their needs are. They develop digital strategies. They do hackathons and involve citizens in citizen science. They may even have showrooms, so-called city labs. So this green part is usually done by cities when we engage with them. We were lucky enough to work with Freiburg, Cologne, Flensburg, and also here in Singapore to come up with the 4 dots in the center. Dynamic data spaces are urban data spaces where all kinds of city data can be collected and redistributed. Cities sometimes have requirements for apps, smart city apps. It can be anything from routing traffic to providing real-time information, but maybe also to collect data. An important part, many cities in Germany want to emphasize road cycling, but it's not easy because we don't have a lot of sensors. So we don't know where people cycle. So people can actually donate data points. They download an app. They agree to share their GPS coordinates. And this enables the city to actually identify where active mobility takes place. We have a lot of requests for AI and urban analytics. So large data sets that have to be analyzed for all kinds of patterns, mobility patterns, pre, during, post-pandemic, changes in energy consumption, you name it. Distribution of, well, I'm going to stop with the examples, but distribution of charging stations, reorganization of fleets. And then we come to the points of knowledge graphs. So this is today's topic, but I also want to say that it's not Singapore, Pirmasens. There are also other cities in Europe that are investigating this currently. And if we put it all together, we're looking at the universal digital twin, which would be the world avatar. So an open source ecosystem, how does Germany go about it? First of all, I want to clarify a little bit where we're at, because depending on whom you talk to, you might have different expectations. Many cities have number 2, the geo-based twin. Sometimes they request number 3, a domain twin, let's say an energy twin, or here in Singapore, my colleagues helped to develop the Cooling Singapore, the digital urban climate twin. You could imagine a digital twin of all kinds of domains if you wanted to. And number 4, of course, there are urban IT procedures. Like we don't need to necessarily reinvent the analog processes or the IT processes. They have to be linked in, and there can be many external data sources or even other platforms. But number 1 is the urban data platform, which is the point that we help cities develop. This is an example of a software architecture that we produced together with CMPG, the CARES spin-off in Germany. And this shows how various components, I'm sorry, they're German, I should have translated them, work together. You don't need to see and study all of it, but what's important is that there's a horizontal layer, which is an identity and access management, and there's a vertical one, which is a data catalog. And the standards for these catalogs have been developed jointly across the EU, and they're compatible. So it doesn't matter who's starting to fill in the catalog, they will all be in the linked open data format, and they're ready for semantic web technologies. So what have we done since 2 years since I joined? We have worked with 4 cities in Germany, Freiburg, Traunreut, Landshut being in South Germany, in Berlin, to develop various forms of twins or data spaces. We've worked with the German government to build a digital stress test or urban resilience monitoring tool. We've analyzed mobility patterns, and we've done conceptual studies. And gradually, I would like to expand in both sides. I think the strategy development is very interesting as well, although there's a lot of competition. But once the strategy is set out the right way, it will point back into the applications. And of course, I want to further develop the smart city solutions with the knowledge graph technology and the insights that we were working on together. So this concludes my talk. I just wanted to quickly introduce Arup. You may have seen some of these buildings. Arup has almost 80 years of experience across the world, and we're now working in Germany across 4 places. I'm located in Berlin, but I was also very happy to meet my colleagues this morning in Singapore. So if you're interested, feel free to reach out. Thank you.
Thank you, Aurel. I suppose you're one of our KPIs, okay? You managed to reach this great velocity from academia to the real world. And so I'm super happy that your employer let you come, right? And that we basically confirming that the work we do is very timely, and that you, like it looked like that there is plenty of demand at the moment and even more to come. Is that correct? Yeah.
Yes, thank you, Markus. First of all, I don't bite and I'm not contagious just because I switched sides. But on the contrary, I really enjoy being back here. And I think it's the spirit of transdisciplinary research to bridge the gap between academia and industry. And yes, I really want to stress that there is plenty of opportunity. A week ago, I was in Amsterdam meeting with my Arab colleagues for a digital urban twin go-to-market workshop, which sounds very businesslike, but it's from Milan to Madrid to Dublin to Amsterdam that cities are approaching academics, but also engineers in order to help them do this transition. So it's not just in Germany. Why is Germany and Europe of relevance for Singapore? I want to give one example. The high standards for data privacy, which were developed in Europe, became the quasi gold standard for developing software and digital solutions. So I think this open source approach is also very interesting in the Singaporean context. And I'm curious to see how it is going to be adapted here.
Right. Any questions, Lena?
Hang on, we can do this.
I've got 2 questions here, one with regards to the project and the other one with regards to Arup. The first one, the project, I noticed that the emphasis is a lot on climate change, very little on tracing timeline targets of biodiversity. And I think we've been talking a lot saying that almost all biodiversity solutions are good for climate change, but climate change solutions are not necessarily good for biodiversity. So why the emphasis on climate change but not on biodiversity? So that's the first. And especially, people talk a lot about Paris Agreement, but nobody talks about the Kunming Montreal Global Biodiversity Framework, which has targets that are actually relevant that you all can contribute. So that's the first question. Do you answer that first before I answer that?
I'll answer it very briefly. You're spot on. Biodiversity loss is probably even is a bigger challenge than the climate change. I have put up the European Green Deal and the latest report by the IPCC. So it's their wording, not mine. But Arup as a company is embracing green solutions. We call it Nature Plus. So the idea of an augmented nature, a nature that includes humans but is not anthropocentric. In terms of design principles, there's quite a lot that we try to do. When it comes to digital transformation and smart cities, I want to give you an example that I really like. A city in southern Germany, Kirchheim, installed audio sensors that are so sensitive that they can pick up road traffic, human noise, but also birds and insects. So the sensors doesn't care what spectrum they're picking up, but they can sense, let's say, the activity of insects and also birds, which is an indicator for the well-being of the biodiversity in that city. So this would be a link where, yeah, almost like a byproduct of a technical problem, let's say noise pollution by traffic, also has the possibility to include biodiversity measurement at no cost. Another one in Berlin where we're not working on, but which is very popular currently because it's very tangible. Trees in cities suffer a lot from the so-called urban heat island effect. So it's too hot, it's too dry. There's a risk that these trees die. So a mixture of remote sensing and AI helps cities to target the trees that are in distress and water those during certain periods of drought, because you have to be very selective which ones you kind of, save and which ones are okay by themselves. So the link is there. Second question?
Yeah. Okay, thanks. Probably talk to you a bit more. The second one is, I spoke to Pieter Herthogs, who used to head Arup UK, and what he did was that he was involved with the Dongtan Eco City project, urban work project. So is Arup doing a lot more working on planning, master planning, and development of eco cities all around the world? There's it's something that is there are so many cities, and what we want to do is to ensure that there's biodiversity in cities.
Yes. So this particular project is already a bit older now. I believe that because it's already implemented, so maybe the planning dates back 15, 20 years. I'm not exactly sure. So this morning I visited my colleagues in the Singapore office, where, as probably every office in Singapore, covers a huge geography. For instance, they're working on the master plan for the new Indonesian capital. And there they've integrated the sponge city concept, so the water sensitive urban design, biodiversity concepts, and of course all the suite of sustainable design concepts. I don't want to segue too much into what good planning could be. I would like to say that it's important to have an evidence base for your design, and this is where the city's knowledge graph and the semantic web technology comes in. Because, as you mentioned, what is an ecological city to begin with? Yeah? You have trade-offs. There will be space given to humans, there will be space given to nature. They have to come together at some space. There will be an interface. There will be, there will be some space for the cobra, but not the whole city will be accessible for the cobra. And there was some space for the humans, but not the whole space. So that type of negotiation is something that in the past was done by a select group of people, called themselves experts, and it was set in stone. So many of the cities that were planned from scratch, like Brasilia or Chandigarh, were criticized for that. Whereas now we have the possibility to design cities together with people. And not just that, the city is a very complex and also slow system. Once you determine the plan, there's a path. And you might be on a path towards the second slide that Professor Kraft showed earlier, to the kind of dystopian future without even knowing it. So you need a system like the one that we've shown in order to show you what the future scenario is going to look like. So choosing between dystopia or utopia in the past was guesswork, and now it's a little less guesswork. Yeah, I'm not, but I feel like you have more questions. So
There's one more.
Hi, one thing I'm curious about is one thing I'm curious about is that a huge barrier towards data sharing and open source data in many contexts in the world is how many actors are reluctant to share data because of grounds of data privacy and national security. And I noticed that Germany, as you mentioned, has gold standard data privacy regulations, but also seems to have a thriving open source community and also a more of a willingness to try more innovative data sharing practices. But I'm sure this also comes with challenges. I'm curious how, in the German context, how you ensure buy-in with stakeholders, how data is shared, how you convince people to share data, and if it's translatable to other contexts like in the countries where my project is working on. Thank you.
Yes, thank you for this question. So the first thing to understand about linked open data is that you need to have an access and identification protocol in place. So the reluctancy of sharing data stems from the threat of somebody misusing, stealing, or transforming the data. If you have a protocol in place that tracks who's accessing it and for what purposes, then that threat is resolved or dealt with. So of course, not every data set needs to be open, but having a standard like the one developed in Europe currently enables you or a city to broadcast data and to share it. And as we know, a single data point is kind of trivial, but and not very valuable, but connected data is. And this is where the idea of a common data repository or data as commons comes back. And the European cities recognize this, and they're willing to provide the backbone, the infrastructure, the standards, and so on to facilitate it. So I think we need a bit more. Yeah, I can see many points where many cases where data may not be linked or open, but in the case of cities where it's about planning for citizens and resolving some of the tackling challenges, the value of open data should be recognized. So I'm saying that it's really a cultural approach. It also requires a governance structure. I didn't talk about that, but if, let's say, the governance structure is data governance structure is set not to publish and to keep it siloed, you can try as hard as you want. Yeah. So the development of the appropriate governance structure, data governance structure, is also a prerequisite for this.
I would like to add a few comments to that. There is now both in Germany and the UK, there are initiatives to do something about that. In particular, when it comes to the smart meter network in the UK and Germany. So in Germany, the Bundesinnenministerium, which is this super agency that also does, I don't know, Wirtschaft and what is it called? Wirtschaft and Umwelt or something, yeah. So they have a big initiative to pull data from different sources and share it, and they create platforms at the moment. And in the UK, something similar happens, although I would say the UK is even a step ahead, in particular with respect to the smart meter network, which will be of big importance when it comes to these load predictions, and particularly moving into a world where you have EVs, you have batteries, you have local solar cells, and you then have the prosumer, you move over to the prosumer, and of course, at that point, it is absolutely important that you have a completely digital or sort of information model of all the individual entities. What we are doing here are the first steps towards this. And I will show a few examples in a few minutes that highlight this. Any more questions for Aurel before he checks off back to Germany? Okay, this doesn't seem to be the case. I would like to use this opportunity and express my deep gratitude to Aurel, because this whole project wouldn't exist had we not had very early discussions. In fact, the first time Aurel and I met was at the German Wissenschaftler-Stammtisch, which is
Still exist?
Yeah?
Does it still exist?
Yeah. It's still going strong. Okay, and so the German embassy organizes a get-together once a month for everybody who feels associated with the German Wissenschaftler. If you feel that you're really a German Wissenschaftler, you should come along, because that's all you need to do. Feel like you would want to have a beer and potentially a sausage, because we always pick places where you can have German food, okay? Which explains why I am a regular visitor to this, okay? And this is where Aurel, it was in Vivo City, I do remember this, yeah, where we first met. So Aurel, I think it's great that you came all the way here to basically complete our mission. And yeah, round of applause for you. Thank you, Mark. Thanks, everybody. Right, okay, so at long last, it's my turn. You have already heard, so you have already heard of some of CNPG. This is computation modeling Pirmasens, and this is CMCL, computation modeling Cambridge, and COMO, computation modeling group in the University of Cambridge. That is, these are entities where I am involved in, and of course CARES, which is the direct partner of SLC. And so Peter gave you sort of the in-depth study, going through one or two examples of ontologies, explaining the details and so on. And so what you now see is much thinner, but of course it is much wider. One of the key points of ontologies were that they are basically knowledge representation. And as such, there is no specific field of application. Any field of application, any thought, any concept can represent it. And because of that, we chose a name that is inclusive. And so, so we are talking about the word avatar as an idea. And so here the world is not planet Earth. Here the world is something, is basically the set of all possible concepts that you can imagine. And if you think about what your world model is, if you close your eyes and you think about the world, then you will see that at least conceptually, it is basically like the word avatar. So now what we do here is, and this is the title, augmenting reality. So what does it mean? If you look in this room, you see chairs, you see walls, and so on. But there is nowhere written that these molecules are actually a chair. This is something you have decided. Okay, this is a concept you use to make sense of the world. And this is what we are now doing here. Okay? So what can you do with such a representation? Okay, for a start, you can connect everything with one another. You can once you have connected, and Peter showed a fantastic example, you can search, you can query, okay? But once you have also live data in it, you can control, you can make this thing actuate certain control. And you can also imagine, you can have the word represented as it is, and then you can, with the power of your imagination, okay, if you look at me with the power of your imagination, you can imagine I'm wearing a hat now, okay? And then I walk around, and in your imagination, I'm still wearing this hat, okay? So your imagined world and the real world, so to say, they are connected to one another, okay? And that makes the scenarios in the word avatar different to normal scenario study. In a normal scenario study, you freeze the word at a certain point in time, and then you compare it, okay? But then if the word moves on, your scenario is outdated. But this is not the case in such an environment, okay? Okay, so the second thing that's important for me to tell you is that we try to think of the world slightly differently. And I call this here a change in perspective. If you think about, okay, we've talked about ontologies and all that, what does that really mean? What consequences does it have if you really think through it? Okay, so many people talk about human in the loop, and how do you deal with the internet and technology? Then very often somebody tells you, okay, you go and do something, and you decide, or not somebody, you decide, okay, I want to clean my flat because it's Saturday morning and that is what I do, okay? So my aim, so you can ask, why do you want to do it? Because I want to live in a clean flat. So it's a goal. You have decided, this is my goal. So this is the why. And then, of course, you know how. You know, you have to go to the broom cupboard, get the vacuum cleaner out, and start cleaning, okay? So this is the vacuum cleaner. This is how to vacuum clean, okay? And so everything is mixed up, the why, the goal, and the how. But if you have not just data, but also a knowledge representation, these two things suddenly split. And you are in a world where the why, that's still you, okay? You have now two roles here. You give the goals. You give the goal to the system. But the how, that is in your knowledge model. You don't need to know how to do a certain thing. You just need to know, okay, I want to be rich and beautiful. And the rest is done by the word avatar. That's great, okay? So, or make it a bit easier. So I was asked the other day to bake a cake. And baking a cake, fantastic goal, great. Okay, unfortunately, I can't bake a cake. So what do? I go to Google, download the recipe, and then follow the recipe. So now the how came from Google. Okay, but I used still knowledge to query the website, to read it, and to transform this into individual steps that make me bake a cake. So it's sort of an in-between world, in the world where the word avatar is connected to handlers or to things, or even maybe to a human, then the instruction can be far more detailed, okay? And they can be instructions that go on into machines directly, maybe a cake baking machine, or to a human like me who is trying to bake the cake, okay? So, but you have to have, in order to be able to do this, you have to have certain abilities. So one ability is that, okay, I told you just I want to be rich and beautiful. So the next question is, yeah, okay, this is all good, Markus, but how do I achieve this? Okay, so then you have to, and we have a big knowledge model, and now you have to go through it. And so the knowledge model would say, if you want to be rich, you have to work hard. Okay, then that would be bad news, because the world avatar would say, Markus, do you know what? I have to break it to you now, you have to work hard. So I would go and work. Okay. But then, oh, you want to be beautiful. And then the world avatar tells you, Markus, you better start your exercise regime. Okay. And now you know why it hasn't happened. Okay. So, but here the point is that, okay, the knowledge model, there was a process in that world avatar that broke down a general goal into individual sub goals. And of course, in the planning area, if you want to automate things, then that will also happen. And then finally, you know, if you represent the world changes. So for example, somebody left the lecture theater. The number of people here has changed. Okay, so how, if you have a knowledge graph, how do you represent them? And this is where the derived information framework comes in, because just like our brain, we have sensors. You know, how did I know that somebody left the lecture theater? I saw it. Okay, I saw it. I interpreted it, and then I sort of subtracted from the people one person. And this process needs to travel through your representation, and this is done with this model. And these two things make the world avatar stand out over and above standard knowledge graph technology. So these are add-ons. Okay. So now when you do that, and what I try to do here is make the point that it's really open, an open environment. So you can start from any scale. So here we do potential energy surfaces using quantum chemistry. These are already implemented in the world avatar. Or we can create new molecules with better properties, because we have now access to the knowledge space. So this is not just like AlphaFold, where we use lots of data to then predict chemical properties. This is sort of making use of the semantic representation of specific molecules and their fragments and specific reactions to propose new structures. Then we can represent buildings, and you may have seen earlier the representation of our laboratory. Here you see representation of building information model. So we talked a few months ago to LCA, and if you now want to approve a building, then you have to supply the building in form of a building information model. This now can be automated and immediately integrated into the knowledge graph, which of course then gives other agencies a much better model to work from. But it's not just the building information model, it's also the building management system. So the live data that describes the state of the HVAC system and so on. And of course, within the building, there are individual devices, they can also be described. So I will now have to speed up a little bit. As I said, we have the energy systems. We even can perform chemical experiments. So this corresponds to the automated scientist. And in fact, what you see here, these are two robots, one in our lab here in Singapore, one in the lab in Cambridge, and they work together on optimizing one specific reaction path with respect to the yield and cost of this chemical reaction. So that went across half the globe, completely independent, all as part of the world avatar. But you can extend this much more, because the lab is not only a place where you do science, the lab is also a place where you have assets. They need to be administrated, they need to be tagged, and we have introduced the asset tagging system with RFID tags for example, here for flammability. Now, this is a building scale, now more domestic. So I grew up in this house. This is my room. My wife calls it the Marcus Museum. So we basically instantiated this in my hometown. You see here the other houses. But we are not just in Pirmasens, we are moving also to Singapore. And what you see here are the evolution of NOx at the harbor front. Okay, so here, this is a virtual sensor. And so you have here the time, and you see that in wind changes, that once in a while you get significantly high NOx emissions. Okay, now we can put these sensors all over Singapore, all at the same time, live, right? So, and not just Singapore, anywhere in the world, no problem, right? And we've done that, and then we thought, okay, I have not enough control over my students, so I thought they have to be instantiated in the world avatar so that I control any movement. Okay, as it turns out, the students take time off and walk in Marina Bay, in the gardens by the bay, and so my student walked around this yellow park here, and these modern mobile phones, they measure, for example, their position, like GPS. They measure speed, light. Okay, here my student must have put the mobile phone in his pocket because it's completely dark, and there is a little bit of noise. I don't know what happened. Okay, so anyway, there is also the mobile phone is now connected to the world avatar, and can of course augment the readings in the phone with humidity, temperature, and UV index. So this has been, so this is a sort of a soft sensor. But on top, I told you about the dispersion simulation from the ships. We can now also at any point in time look at the virtual emissions that are received at this point of NOx, ozone, sulfuric oxide, and particles. So this is now with your phone, and my students could basically, while he was trying to escape from work, could actually monitor the environmental conditions, and suddenly here. At this point 3, he discovered that there are unhealthy particle emissions, and at that point, my students decided, oh, it's not worth running around. I better go back to work, and then he partly immediately went back onto the MIT and back to Privet. Okay, so with it, I'm just looking at the Shinza, who actually took the measurements. Okay? So, anyway, this I augmented the story a little bit. Right. Okay. So this is one thing you can do, and so now we are working with PNL. So here we want to do route optimization in waste collection. We want to basically using weather data, live traffic data, client and day in order to basically help to optimize waste collection. We also work together with NTU, and these are not researchers, these are actually the people who are responsible to run the whole campus. And here you see, and there's also an example outside. Here you see a heat map that tells you something about the power strain within NTU. Different colors of the buildings mean different meaning. We connect it with class schedule. We have live data, and the idea is that we now, for example, if we know there is a class schedule, we can of course change the set temperature for the air conditioning system, so that while nobody's using the room, maybe that the temperature is a bit higher, but before the class starts, the temperature lowers a bit, and through that we can overall change and basically reduce the energy consumption of the building. Okay, and so just as mentioned before, we can take a whole lot of heterogeneous data, weather, buildings, photovoltaic, historic loads, glass schedules, and many more, and then use forecasting agents. And this is where classical machine learning comes in, and visualize, monitor, and control what is going on. And this is something we have developed for our building here in Create, but also are about to do for NTU. And of course, as you can imagine, this is relevant for any other building. So now we could do it for each HDB building in Singapore. The moment you do that, data collection, load estimation suddenly becomes easy because everything is available to everything. So, so this is a revolution we are facing, which will completely change the way we operate and accelerate our ability to change and mitigate problems enormously. And again, here, my hometown, this is Pirmasens, one of the poorest cities in Germany, but it's really beautiful. So I can only encourage you to go and visit. So this is, I was sponsored by the tourist board, so I have to say that. Okay, so anyway, you see houses with different colors. That is a different meaning, and the color indicate different uses, and then you see a color coding here, and these are isochrone maps for pharmacies in Pirmasens. It basically tells you how far, how close you are to the next pharmacy that's open. And the beauty, of course, is on a weekend, when you have an emergency schedule, then you immediately know, oh yeah, you have to go 10 minutes or whatever. Okay, this is a relatively simple use case, but a nice color picture. Yeah. A much more sophisticated use case is the control of the district heating network. So this was together with Stadtwerke Pirmasens, and we got about 50 award for it. And the work was done by Markus over there. Yeah, here, yeah. And it's actually quite a complex optimization problem, and was very successful. And now moving on, still Markus's work. This is a flooding scenario from King's Lynn, where we were able to connect different areas, different data from completely different data sets, Met Office, Land Registry, Environmental Agency, Ordnance Survey, and so on, to be able to see the impact of an extreme weather event on the overall infrastructure and people. And now we combine this view with the routing earlier on. So if we have a flooded city, in this case King's Lynn, we can then also create the isochrone map and are able to identify how many people are now cut off in a matter of seconds, right? But it's not just people, it's also infrastructure. Here we work in the Credo project as part of the National Digital Twin Hub in the UK to see if we have a flooding, maybe say a power station goes down. This power station feeds a number of pumps. This power station feeds a number of mobile phone masts. So the question is, once a power station goes down, what infrastructure is switched off? How many people are without a phone? How can we reach these people? Where do we have to send emergency services? And finally, we can also large countries. And what you see here are the first steps of a digital twin in Chile. For that, you need to know that Chile policy for the future is to be a major, they want to be what Saudi Arabia is now for fossil fuel. Chile wants to be the Saudi Arabia for hydrogen. And why can they be that? Because there are strong, constant winds in the southern tip of the Andes, and it's an ideal area to generate hydrogen. And the question is, where do you put it? What infrastructure do you use? What chemical plants should be there? And we will try to help the Chilean government to decide this question. And so these are a whole variety of different scales. How can you interact? So that'll be quick. We have 2D visualization at the moment. We can do 3D. We have dashboards. We plan to extend our ability to interact with the world avatar through mobile apps. And we have a question answering system that was also displayed. I've already made it clear the world, not only the set of all potential concepts, but also any place on planet Earth. So we showed examples of Singapore, Germany, UK, and Chile, and we are now hoping to extend this even further. And with that, I would like to close. And then we have another 5 slides. So bear with me. And then there is free food and things. And if you have a question, please let me know. I'm happy to answer. Nothing. Come on, on which level is the food?
That's a good question. I don't know.
Okay. Okay, I think you're a bit oversaturated now. So let's wrap this up. So, Peter, yeah, why don't you start doing it?
You can finish the story of Neotropolis.
Neotropolis, okay. Okay, so anyway, I think with our super duper technology, we can safely say New Neotropolis is restored. Thanks to our knowledge graph technologies, I think we've got everything under control. And it's a shining beacon of hope and innovation. Well, that's good, yeah. The story of the Neotropolis serves as an inspiring testament of the power of integrated data. So this is our main conclusion. And next slide. We've learned this was made possible because of the knowledge graph resolution. With that, you can talk about predictive maintenance, resource optimization, traffic management, environmental monitoring, and many other things. Okay. Okay, so Peter, are you embarrassed?
No.
Okay, so this was actually go back. Okay, so this photo was taken in the 2020 before COVID.
During COVID.
Yeah, in the Kingdom of Belgium. The Kingdom of Belgium.
Guess who suggested the restaurant?
Yeah, so if you ever feel that you want to eat Belgian food, the Kingdom of Belgium supplies it. Okay, so yeah, that was a very nice evening. So okay, well done us. Okay, next. Right. So what is next? Clearly, this whole idea of the world avatar hasn't come to an end. In fact, it's completely open. And if you go to the website or just type it into Google, then you see that leads you to a web page that tells you also how to interact with it. In principle, there is a huge GitHub that gives you access to all the software. It's still work in progress. It's not easy to use. It's not to the level of easy entrance as we would like to see it. But anyway, just keep your eyes on it. And with that, I pass the microphone back on because I can let Pieter say the last words.
The last words.
Yeah, it's enough.
In that
last
sense.
words.
Yeah, to finish the story, what's next? There's many future problems that these heroes that we met can solve. They will start an international network of like-minded heroes because that is necessary for this endeavor. And they will face new and exciting villains like Dr. Net Negative and mediocre urban design man. And many of these heroes have started their own spin-off adventures. That is the wrap-up of our story. Thank you for joining today. And again, you've seen all the work, but it's been the work of a lot of very nice and talented people. Thank you for coming. Thank you for joining us. And we shall move to
Level 10.
level 10.